So this is, your fifth day with the FDP. So you must have come across, varieties of subject related to electric vehicle. Is my voice clear, sir?
Yes,
Fine.
sir.
Okay,
Your
great,
voice is clear and also your screen is also visible.
great. Okay. So basically, battery electric vehicle. You must have touched lots of topics related to motors, aerodynamics and all. So I have given today's opportunity with one of the subsystem which is related to electric vehicle and quite crucial part of the. So before I start, let me touch some of the so you must be knowing this dashboard, that is our Tata Nexon EV. It seems very attractive, and people used to have EVs based on the look rather than the ratings of electric vehicle. So let us see what is electric vehicle. Electric vehicle is nothing but a vehicle which operates basically on battery, right? So there are some terms related to electric vehicle, which is said BEV, which is a battery operated electric vehicle. There is also term HEV, that is hybrid electric vehicle, and there is also said ZEV. You must have heard about ZEV, that is zero emission vehicle, right? So there are various electric vehicle which are concerned based on the medium of travel, where mostly people are talking about the road electric vehicles, generally two-wheeler, three-wheeler, four-wheeler, but it's not so. The scene is different. The scenario is changing from developed countries to developing countries. Basically, electric vehicles are not only constrained to roads, but that also involves the rail, also involves water system, also involves the air like drones, helicopters, etc., pure solar based aeroplanes also. So electric vehicles are only roads, so that is what I want. If we see into detail of electric vehicle, it's a system. Electric vehicle is a system in which input is basically our electricity, either in the form of battery, that is stored electricity in terms of chemical, and the output of electric vehicle system is nothing but the traveling or the distance or the acceleration or the velocity, right? So that is a system which is basically electric vehicle. So electric vehicle is a system in which input is electricity and output is the travel distance, right? So in electric vehicle, there are various subsystems covered. I hope you must have touched various subsystems so far, and those subsystems deals with mechanical also. Some of them are related to electronics also. Some of them are related to purely based on the look, that is the designers of aerodynamics, etc. Let us see the subsystems of electric vehicle. Is my screen visible, sir? Is that okay? Or
Yes, sir.
okay. So in complete electric vehicle subsystem, if we see in detail, there are three subsystem classified. Mostly this is the model being used. This is, I'm talking about pure electric vehicle and not hybrid one. Okay. This is electric propulsion subsystem, in which mostly all the conversion is done from electricity to the mechanical system, that is our transmission. That is what we say as powertrain. Okay, and the inputs are brakes and acceleration, and based on that we have our power converters, and from that the motor is running, and ultimately we have the speed. Another system, that is energy source subsystem, where we have our energy source, okay, where we have refueling of the energy source and the management of it. Fine. There is third system, which is said auxiliary subsystem, in which we have all the facilities and comfort zone, where we have AC control system, our media, that is audio system, music system, okay, and the power steering is also there. So auxiliary subsystem is there. Why I'm talking about all this is because energy source, energy source is to be considered based on auxiliary system also. While we play music at high volume, it is also going to be considered as load on the battery or the energy source within the vehicle, right? So whatever auxiliary subsystem is there, as well as the need of our traveling is there, based on that we have the demand, the design, the ratings of energy sources, right? So today what we are going to see is the subsystem, which is energy source subsystem, right? In detail, if we see energy source subsystem, that is whole system is electric vehicle. Inside that electric vehicle, we have one subsystem, which is energy source subsystem, in which we have energy sources. Well, energy sources can be your fuel cell, it can be your battery, it can be hydrogen, it can be anything. So based on that, the energy sources, our energy source subsystem is going to be considered as design part. Fine. Then vehicle controller, which is connected to that. Okay, so a vehicle controller which has also input, that is brakes and acceleration. So based on that brakes and acceleration, our vehicle controller either braking or the speed or pickup we can achieve. But the command goes to the energy management unit also, and ultimately which is going to take all the current power from the energy source, right? Well, vehicle controller depends on your basically two-wheeler, three-wheeler, and four-wheeler, and the drive cycle at which you had designed your electric vehicle. The driving cycles are some standard driving cycles based on which you have acceleration, and the time scale is there, and that cycle is repeated. So in that case, we have intra-city cycles also and intercity cycle also, in which we have FTP 75, which is a standard vehicle design cycle to be considered for designing the vehicle. Then another component comes, that is charging converter, which is nothing but our energy refueling unit. And in that case, we have varieties of chargers available nowadays, like Bharat AC 001, Bharat DC 001, So based on that, various chargers, type A, type 1, type 2, type 3, okay. Bharat DC 001 is basically up to 15 kilowatt capacity and above that. So basically, there are slow chargers also and fast chargers also, in which energy sources are basically playing crucial role while designing the chargers. Okay, in that case we have to consider with whether it is slow charging expected or fast charging expected. Well, energy management unit is there, which is going to be touched today, and today's topic is that is our battery management system, right? So whatever you had touched so far, today we'll see about battery management system, which is nothing but management of the battery only. So today we are going to talk on battery side only. We are not going to touch the fuel cells. We are not going to touch the hydrogen management or either regeneration, etc., etc. This is one of the pick which is from Mahindra Electric Reva. Here, whatever you are seeing inside this battery pack, it is only batteries, right? And these batteries are designed and formulated such a way that you can have your potential, sufficient potential, and you can have your sufficient current rating also. But battery management system is not there. The picture is not showing any part of battery management system. it is available externally. So in the first electric Reva at India, that is Mahindra Reva, that is having a battery management system outside this battery pack. Okay, so let us see it. This is today's timeline, in which we'll see about battery design and its parameter. Okay, battery modeling, need of battery management system, how to do simulation for BMS, how to select the hardware, what are the softwares required basically for hardware consideration of BMS, and testing of BMS, what parameters you have to test after design, and if anything is left, we'll discuss on BMS design, right? So today we are going to see this. So energy storage system, as I touched earlier, it has electrochemical storage, electromagnetic storage, thermodynamic, and mechanical. Out of this, this electrochemical and electromagnetics are part of this system, that is battery management system, in which you have to understand how your battery is designed, because ultimately you are managing something, so you have to understand in detail what is happening with that. Okay, if your batteries are lead acid, nickel cadmium, nickel metal hydride. So based on your battery cell, okay, it is going to differ the design, right? Basically, battery is nothing but made up of lots of cells, right? So a single cell which is going to make a battery pack or a battery module or battery system. So that is to be considered over here. There is another batteries, that is vanadium, zinc bromide, and there are hydrogen systems also with fuel cells. In case of electromagnetics, we have electrostatic supercapacitors are there, and supermagnetic energy storage systems are also there. I hope you must have seen that advertisement of battery, in which the drink is given. A girl who is expected to start her vehicle cannot be started because the battery of the vehicle is discharged, and a guy is coming and taking a drink and then just plugs in, to the girl, and immediately the vehicle is start. So basically, is it possible that from external source, like taking a bottle of drink, which is going to give you electrostatic charge? So definitely some electrostatic flow is there, which is controlled over there, and that is nothing but our battery management system. So in which you have either the need, which is immediate, okay, it may be the slow need, it may be the losses, etc., etc. So basically, energy storage system is what is the need and why do you need, when do you want, and where do you want. That those things are very important, because we had seen the battery storage systems basically at various substations also, right? We had seen battery storage system at our home also, at our two-wheeler, gasoline based vehicle also. So based on that, our battery system is demanding different things, right? Okay, and let us see this video. If the voice is not audible, please let me know. Can you see this? Sir, is it visible?
It is visible.
Yes, sir.
Yes, sir.
Yes, sir. It is
See,
visible.
can you hear the sound? Can you hear the sound?
Sir. Yes, sir.
No, can you hear the sound of this video?
No, sir. No.
No, sir. No, sir.
Sound is not there.
Okay, let me go by my way then. Basically, the design of battery storage system is, first of all, you have to find the purpose of your battery storage system. Why do you want to design your battery storage system? So it can be any of this application. It can be the cloud storage system, that is for server. It can be for the space requirement, that where you have to depend, the large number of cycles cycles and recharging facilities. It may be for video recording. It may be for pure electric vehicle. It may be for oil pumping station. It may be for train. Even it can be for your hair dryer. So battery storage systems are available all places, and all places demands basically two things mainly. What we see is that is voltage and the current capacity of it, right? So how much amount of current you require, what is the current versus R graph, that is AH capacity, which is going to be expected, and defining based on the purpose of your battery storage system. The first step comes, that is how to do all this calculation. So for that, you should have to plot current versus time and voltage versus time graph, right? So current versus time and voltage versus time graph is basically on your need. So on the basis of the need, you will find at initial stage how much current is expected, and throughout the cycle. So basically, if your application is electric vehicle, so initially your current expected is high, while running it is low, and slowly during the braking it is going to be zero. So based on current versus time graph, you will be able to find, and the cycle R, the maximum ampere expected from your storage system, and the minimum voltage expected from your battery storage system, because it is going to run the different systems. So based on that, you have three main parameters, that is cycle R, maximum ampere required, and the voltage, right? So in battery, we have varieties of rechargeable, and sometimes we don't go for rechargeable because it's very costly. So we prefer to have use and throw system also. In that, in detail, if we see, then there is a two classification said, that is primary cell and secondary cell. So based on the primary cell and secondary cell, now lots of cells are available, in which you will find that the single cell parameter is quite important to understand while we design overall battery pack. That is voltage, ampere hour, and the power rating of the cell. And now based on this particular cell, we have different criteria. In that, what we see is, if you are expecting some voltage from the battery storage system, then we have said as voltage funda. In that, voltage funda is basically the combination of series potential of the cell. That means this cell potential plus these, as most of our participants are electrical side, so it's very much understood that series connection will add voltages, right? Let us say V cell is of one cell is 1.8 volt, and the overall battery pack expected is 48 volt, right? So number of cells required in one path is going to be what? That is NS is equal to V total, that is 48, and divided by V cell. So ultimately you will find the number of cells to be connected in series. Okay, this is one layer of battery pack, in which you will find number of series voltage, and that is through voltage rating of overall battery pack. Fine. And suppose we want to go for the current rating. Okay, so in that case, of course, what we do is we go for parallel funda, that is the current funda. So in this case, if your overall current rating expected, let it come. This is the video, I cannot break in between. Just a second, it is going to come. So this voltage funda will give us, the series combination. Let us say 6 volt, 10 ampere is there for a single cell, and you want the combination of 12 volt, 10 Ah. Then we definitely go in with series combination of your battery cells, right? So now in case of current, what we expect is it should be connected in parallel, right? So parallel connection is going to add the ampere. Okay, let us assume that one cell is of 5 ampere hour and the expected battery pack is of, let us say, 100 Ah. Okay, so if you want 100 Ah, if your single cell is of 5 ampere hour capacity, then total number of cells to be connected in parallel is I total divided by I cell, right? So ultimately the total 100 ampere hour you can draw out from your battery pack by connecting them in parallel, right? So this is the internal side of your battery, in which the same cell is there 6 volt 10 Ah, but if I connect them in parallel, I'll have 6 volt 20 Ah battery pack. Now this kind of combination you can do based on your battery voltage rating, right? Out of that number of series and parallel connection, you will come to conclude the total number of cells required for your battery pack. Fine. So this is the overall battery pack design. This is somewhat fundamental. There are so many things you have to consider in your battery design, but this is the total construction of your storage system. Apart from this, there are many things are related. That is number of cycle, cost of the equipment, weight and volume, the discharge rate, okay, heat generation and dissipation, the charging method which you adopt, that is your constant current or constant voltage, pulse charging, based on that also your battery pack is going to be affected. The how much amount of ampere you want to draw, that is hours of usage, that is one cycle use, and whether you want your battery storage system recyclable or not. People are talking about battery swapping stations also. So in that case, the design will be different. Okay, so this is something for design of battery storage system. Once our battery pack is ready, that means we know voltage rating of our battery pack, we know the ampere hour rating of the battery pack, and the power rating of the battery pack. Once these three things are known, almost simple design has been done. But the question comes: is there any parameter to be taken care for a battery storage system? Okay, is there any parameter to be taken care? Yeah, of course, there are many parameters and which are constrained for designing of battery pack. These parameters are nothing but, you should say as that is your ampere hour capacity, weight, volume, C rate, and life cycle. Okay, the life cycle is nothing but it's a number of discharge and charge cycle the battery can handle at a specific DOD, that is depth of discharge, generally 80% before it meets two specific performance criteria. And the DOD and SOC, that means your life cycle depends on DOD and SOC. But apart from that, it depends on the temperature at which it is working. It depends on the state of health, that is nothing but aged capacity divided by rated capacity. Okay, and it depends on C rate also. Okay, so before I proceed, let me give an example that if C rate, let us say 1C is there. Okay, so in case of 1C, this means that at least 10% of charge is required. If my ampere capacity is, let us say, 20 Ah, okay, and my C rate is 1C. So in case of charging, minimum amount of current required for my battery pack is going to be 2 ampere. But if it is 200 Ah, then it is going to be 20 ampere. If it is 2000, then minimum amount of current required to start the charging of battery pack is 200 ampere, right? So if it is 2C, what happens? If I say my battery pack is of 2000 Ah and the 2C, then definitely 20%. That means minimum amount of current to get the battery pack charging state. That means from sleep mode to awaken mode of your battery, that is going to be 400 ampere. Okay, now what happens in case of 38Ah? If my battery pack is of 38Ah and if it is 2C, then definitely how much amount of current is required for charging, right? So 20% of 32H. Okay, you can simply calculate them. Well, SOC is nothing but remaining capacity and divided by the rated capacity. So here basically, and this just a minute, let me change the pointer. Okay, so SOC is based on AH, okay, and it plays crucial role. DOD, that is 1 minus SOC. If your SOC is in percentage, DOD is going to be in the percentage. So that is how 100% is there, DOD plus SOC. Okay, and as age of your battery, when I say age of your battery, whether you are using your battery pack or not, the capacity is going to change. Okay, so some people has a consideration that if I'll not charge and not discharge my battery, the number of life cycle, but it's not so. The life cycle depends on the SOH, that is state of health of the battery pack, and definitely SOH also depends on the aged capacity. That is nothing but the life, from the date of manufacturing to the time when you are using your battery. Okay, so basically this some criterias are you have to consider while you are designing the battery management system. Okay, of course, and the weight and volume are there, that is part of electric vehicle designing, and you have to keep the records, you have to keep the memory of your all the data with BMS, right? Well, apart from this, let us see, just touch as it is there. Rated WH capacity is nothing but rated AH capacity and rated battery voltage. So if my battery voltage is, let us say, 48 volt and AH is 100 AH, then it is going to be what? 4800 watt hour capacity of my battery pack, right? So that is around 5 units of charge. So now let us go further with battery modeling. Okay, battery model is quite important to understand basically when we are designing the battery management system or the energy management system for EV. It is also important to understand while you are designing the charger, and it is also important while you are using the battery, while you are connecting the battery. Okay, that can be with the solar inverter also, that can be with the your electric vehicle as V2G also, that is vehicle to grid communication also, and the reverse also, right? Let us see in detail of the battery model. I hope you must have touched some of these portions, but still as this is important, I am repeating. If it is repeating, let me have the still, because it is important. This equivalent model of battery says, this RP is there. Okay, RP is nothing but self-discharge resistance, which is from insulation resistance. Okay, and this is our basically charging and discharging part. So R2D, that is nothing but internal resistance at the time of discharge. Hello, am I audible?
Yes, sir.
Okay. There is some disturbance coming now. It's okay.
Someone has
R2D
unmuted.
is internal resistance for the charge. Okay, and this says, the direction of your current flow. R1D and R1C is again with that. Okay, the C1 is the capacitance in case of over voltage. and CB is the battery capacitance. As we know, the battery is nothing but like this. Two terminals are there, and if you connect these externally, it is going to have its own capacitance, right? Because anode and cathodes are there, and they are separated by some material that can be electrolysis, and that can be a kind of insulation. So we have a capacitance also like this. Okay, and whatever amount of resistance you are getting at this connection or throughout your wire connection, that is going to be the reason for all the resistances that is input, that is discharge, and that is state. Okay, this is the equivalent model of battery. And while we are considering the battery management system, still go further in the detail. This terminology you have to understand. ESR is equivalent series resistance. EPR is equivalent parallel resistance. Okay, and similarly equivalent series capacitance and equivalent parallel capacitance. Right. So based on the material which you are using, your ESR, EPR is there, and this ESR, EPR is quite important for
Excuse me, sir.
you.
There's a lot of this,
Excuse me,
too
sir.
much of background, sir. Somebody can mute all participants.
Sir, there is so much disturbance. We are not able to hear you. Someone
Sir,
has
please
unmuted.
mute FDP 120. Sir, please mute FDP 120.
Now you can go ahead, sir. Sir, you are not audible now.
Sorry. Is that okay now?
Yeah,
Yes,
it's
sir.
okay, sir.
Okay. Equivalent series resistance and EPR resistance I was talking, that is quite important for losses. The losses occurring into the battery, that is your self discharge, etc. And overall efficiency of your battery pack is dependent on these parameters. So it is quite important. Apart from these equivalent series model, there are different models. Okay, this says my model is battery. Okay, not me. My model, that is battery, says I am the model. Six-pack model of my own, and this is my power. This is my capacity. You can give me thermal stress. You can give me electrical stress. Whatever amount of capacity is there, you can disturb me. Okay, this model says like this. In this SOC model is there, okay, which is nothing but our state of charge model. SOH model is there, that is our state of health model. In SOC model, if you see in detail, the term comes, that is a self-discharge resistance. Okay, that is because of the electrode contact coming. The C capacity, that is our this ampere hour capacity, and VSOC, that is basically open circuit voltage coming to these battery, and the IBAT, that is nothing but the how much amount of battery can allow to flow at open circuit condition. So basically the SOC sub model is quite important because our battery management system will take care of VSOC. Okay. Another is SOH, that is the state of health, in which the state of health, as we had discussed, that is aged capacity and the rated capacity, the ratio between aged capacity and the rated capacity, right? So SOH is a concern, and that depends on the number of life cycle as well as the time period. So when you buy any battery, whether it is for your petrol vehicle or diesel vehicle, they'll give you a guarantee. They'll give you guarantee based on two parameters. One is the kilometer, how much you travel through battery, and the period. They'll say 6 months guarantee only, sir, not more than that. Okay, or you will have the guarantee based on the kilometer, and maybe 2000 kilometer to 2.5, like that. So based on that, your RSOH is there. how they judge, that is because they had tested their battery manufacturing based on the material use of the battery. There are SOH, that is resistance for state of health. Of course, the capacity is going to be the same. Okay. Now, based on this model, you can create your own equation, as you know the KCL and KVL, the Kirchhoff's laws. Based on that, you can have your own equation, right? So this is SOC, which is important. This is SOH, which is also important. And one of the major, very important part, that is thermal submodel. So thermal modeling is also important. And this is the T network connected. It says the environment temperature, how much amount of losses you are going to do in while you are using the battery. That can be in both the cases, right? That can be in charging system also, or it can be discharging mode also. Okay, and CH is the heat capacity. So basically, heat capacity is dependent on two, that what we say as the heat generation. Okay, in case of battery modeling, we have also the thermal criteria, also the heat generation. Generally, it is delta H. Okay, and how much amount of energy, that means heat, you can do or dissipate. So HD is there. Okay, so based on this, how much amount of heat generated within the battery, whether it is charging and discharging, and simultaneously how much amount of heat you can discharge. Okay, so based on that, heat capacity is there. Okay, then thermal resistances are there. Of course, we have to have some thermal resistances, and that is why some of the battery manufacturers have started using the cooling system that can be like our transformer design, that is forced air, water flow, and other liquid control cooling systems also. So this is the thermal submodel of the battery. This is particularly for a cell. Now this is the main circuit submodel, which includes all. Which includes all, where open circuit voltages, which is function of VSOC, and you will get VSOC from this. You will get VSOC from this model. Okay, SOH you will get from this model. And the thermal criteria, that means you will get it from here, that is T, and ultimately your battery current capacity, how much it is expected. So it varies, right? As we know, in electrical, the load is not in our hand, so it varies. So basically, the output of the battery, that is open circuit potential, is the function of state of charge, temperature, state of health, and the battery expected from the, the current expected from the battery. That is our load current. Okay, the remaining is already covered, and that is our resistance and capacitance during discharge. Okay, and this is in case of charge. Why do we have two things? Because one is anode and another is cathode. So two combinations are there. If you are using stack of it, so you have to connect them in basically either in series or parallel as per your model, as per your battery pack is there. Okay. It is quite important to understand, all this terminology comes, the resistance and during the charging and discharging comes from this chemistry of our battery cell. Okay, so properties of these are quite important, and that is what people are trying to use their hand at the chemistry of the battery. And for that you have to understand, because this is quite important in let me go back two things. This is also important. Sorry. Okay, yeah, that is with weight also, and volume also. So based on your material which you had used, okay, which column you are going to use, whether you use this, okay, whether you want from the nickel side or whether you want it from aluminum side, right? So nowadays people are talking about latest battery made in India. Anybody knows the latest battery made in India? aluminum A type, or rather say aluminum fuel cell based battery pack, right? So that is how they judge, basically from this. And this is not my domain actually, the material and the chemistry, but people are trying different combination, different elements to make their own country purely self-sustained in case of battery, right? So in case of electric vehicle, if India is expecting to be self-sustained and self-dependent for the technology, then they should have the motor criteria, that is our the magnets. In case of battery, we should have the material which is lightweight as well as covering less volume but still higher amount of energy, right? So this is how the metallurgy guys and chemical people are trying their hand. If you have any question, you can put into the chat up to here. So this is slide number 15, and up to 15 number slide, if you have any question, please put into the chat. We'll discuss later on. Okay, is that fine, or do you want to discuss at present? Sometimes it happens, no, people forget their questions. So it is up to you whether you want to discuss them at present or you want it later on. Hello, am I audible?
Yes, sir.
Okay, if you don't want to discuss the question as present, you can put into the chat. We'll discuss later. Fine. Let us go further.
Yes, sir. That will be good.
Okay, try your hand with designing a battery pack. I want you to go with this before we start battery management system. Just try your hand. If my battery pack expected is 48 volt and 64 Ah, so using simple, voltage funda and current funda, try to calculate how much amount of cells are required. Okay, and I want response at least from 2-3 participants. Okay, this battery pack overall rating, that is 48 volt and 64 Ah. Okay, the single cell is of 1.8 volt and 6.2. Okay, let me have. Yes, please.
Yes, sir. For 48 volt, we need to connect that 1.8 volt of approx 30 units in series for that to get that 48 volt.
Great. And what about AH?
Yes, sir. For that, I'm calculating.
Is it done? Well,
sir, 11 units.
Great. It's a nice result. Total cells in series is 28 and total cells in parallel. So how much amount of cells you require total for this battery pack? Right, 336 cells. Now, can you imagine the 48 volt 64 Ah with the 1.8? So that means if I want to reduce the number of cells, if I want to reduce the weight of my overall battery pack, if I want to reduce the overall volume of my battery pack, what is the criteria is I have to increase the potential of a single cell, right? I have to increase the AH capacity of a single cell, and that is what people are trying. Lots of people are trying to increase, and this potential has reached, practically reached to 10.2 volt. 10.2 volt. Okay, 10.2 volt, and this 6.2 AH has reached to almost 20 AH. Okay, you can refer some papers of IEEE and IC, and these guys from Vietnam and China, they had developed this kind of cell, which single cell can go to 10.2 volt and a single cell with 20 Ah. Of course, the 20 Ah is around 7.5. Okay, both are different, but this is the maximum
Same
capacity.
X-man battery or different kind of material?
Exactly. So basically, 28 is there, but 7.5 volt. And in case of 10.2 volt, there is another 8. So using different combinations of material, you can have a better, battery pack. And ultimately, you can go with lesser number of cells and lesser weight, less volume, and that is what electric vehicle designers expect, right? Okay.
Okay.
Let us go in detail and the BMS, as the manufacturing of cells has different criteria. Like in our house also, if our mother or wife cooks the food, the everyday taste is different. So similarly, battery manufacturing, that is the cell manufacturing, will have different property. Okay, so in that case, it is quite important to understand the battery management system, how to design. You have to bifurcate the good cells and bad cells. You have to understand the state of charge of individual cells. Okay, and the variation based on the temperature. So many things are there. So while designing the BMS, what you have to take care is, now we are touching the heart of the topic. Okay, uh, BMS is going to read the voltages from cell stacks. Okay, so basically, as we had 336 cells, one, let us say this is of our earlier design, this is 28 cells, one series, and similarly we have another 28 cells. Okay, okay, again this will happen, this will continue up to 12 times. Okay, so overall cell stacks will take care the reading the voltage. That means BMS will take care the voltage reading of this. Okay, voltage reading of this separate. Fine. Apart from this, BMS will have input, that is temperature sensors, current sensors, voltage sensors, the counter of charging. That means how many times you had charged your vehicle, you had plugged in your battery pack, how much amount of current reverse possible, and you can add manufacturers. You can add manufacturers, and some of the volume, with respect to the weight, we had tested the BMS, and the results were excellent. Okay, this battery management system will have, sorry, I cannot erase now. Anyway, the battery cell stack, that is going to be with BMS, temperature sensor, that is connected again with the BMS, voltage sensors, current sensors, and how much amount of power you are drawing from the battery pack. So this is going to touch the battery management system, and overall your battery pack is taken care. There are some objectives for BMS design, that is monitor cell voltage and temperature, estimate state of charge as well as state of health, limit on power input and output based on thermal and overcharge protection. So if your thermal constraint, that means if your battery is in thermal stress, you have to either cut off the supply, or either you have to stop the drawing current out from the battery pack. And control the battery charging profile. So depending on the charging method also, balance the state of charge of individual cells, and isolate the battery pack from source and load when necessary. Right. So this is the main 6 objectives, especially BMS, and people try to reduce the cost of BMS, and hence they may omit. But the main 2 things are there. That is, first one, monitor cells, and second, these 2 are being taken care. If it is a simplest, if it is simplest, very simple BMS, then these 2 things are going to be taken care. Then later on, number of sensors increases, current sensor, thermal sensors, and your complication of BMS raises, and ultimately the cost of BMS is also going to increase, right? Well, as last point has told, that balance the state of charge of individual cells. It covers 2 things, that is active cell balancing, okay, and passive cell balancing. Fine. In active cell balancing, it transfers energy to where the energy is needed instead of wasting it. So while charging or while discharging, it will adjust all the cells to have the equal amount of energy stored. Okay, and that is by inductive charge settling or capacitive charge settling process. Okay, and that is how active cell balancing is done. Well, in passive cell balancing, it is basically the idea to discharge. So if one of the cell is having larger amount of energy and another is at lower, so the larger amount of energy cell has to discharge themselves and make the passive cell. That means, ultimately it is losing your energy in terms of heat. So there will be thermal losses more in case of passive cell balancing, but it's simple and easier to implement. So if somebody from you is trying your hand for designing a battery management system, I'll suggest go for passive cell balancing first and then go for the active cell balancing. Okay. Well, in case of active cell balancing, we have, as said, subtle circuit that is for capacitor. So this is individual component. Okay. And based on that, there are two combination. One is with C1 and another with C2, different. So if your B1, let us say B1 and B2 are there, and out of B2, if your B2 is having lesser amount of energy, so the charge capacitor will give the battery, sufficient amount of charge so that B1 and B2 will be of equal energy level, right? And if B2 is lesser and cannot compensate with B1, so what B1 is do, B1 will give the energy to the capacitor for charging, and they will be at equal stage. So this is how overall your module, that means overall, sorry, let me change it. Okay, so this is based on your overall pack of series combination. Your capacitor settling circuit will help you to make them at equivalent stage. Okay, similarly, there is inductive converter cell balancing, which is a kind of isolation given to individual cell, and that is switching on and off, but that is with inductive charge, right? And that control command is given through the particular cell monitoring, that is overall cell monitoring here, and it can extend up to the number of cells required. But in this case, what happens if let us say B1 and B2, there are two cells, and B2 is of lesser amount of energy. So in that case, B2 will give energy to the inductor, through this. Okay, and it will be reversed to B1 in case B1 is very low. So that means the energy balancing level is can be achieved. But the complication, you can understand that this happens to all the cells connected in the series combination. So if our battery pack is having 300 cells, 500 cells, this complication increases. Of course, electronic guys are there with us. The embedded systems are also there. VLSI technologies are there, and hence we can achieve this very much easily. Okay, so this is what active cell balancing is. Now I'll go in detail. Basically, while we design the battery management system through Matlab or through Simulink, in that case, we have to do some Simulink modeling. That is algorithms for cell balancing, SOC, SOH. Okay, then we have to go with rapid prototyping. So generation of code is there from both the sides. You can go with hardware in loop also, and there will be some protocols based on the communication for that. Okay, and the production code is also there. I had taken this from Matlab only, so don't worry. Let us go to, sorry. Just a minute. Let us go to the battery model from Simulink. Okay. Well, I could not install, this Matlab in my laptop. Just 2 days back, I got a response from Chadasma sir that tried to cover this, but due to my capacity of laptop, it is just 2 GB RAM. I could not upload on the Matlab. I cannot install. But I thought whatever I had tried, I should show you, so that in case of your battery management system design, you can this can be very helpful to you. Okay. Well, this model is there, and there are various models also available in SimSCAP. Okay, if you go to this Matlab links, it shows lithium cell to RC. This is our basic model which you had seen, and it is connected like this. This is C1 and C2. So one is in charging and another is in discharging, and the model is being connected with the reading with SOC. And there is a table given in each case. The C table is given. That is nothing. The table is nothing but a statistic data which is going to give you the value of resistance in case of R1 and R2, and value of capacitance in case of C1 and C2. Okay, and there is a thermal model. Inbuilt thermal model is given. So based on this thermal model, you can run your charging, that is A, V, SOC, and temperature. Right? So you can understand this is individual cell criteria given. So you will have this inbuilt model at Matlab SimSCAP, and you can directly drag and drop into your M5. Okay, in modeling. Generally, in battery management system, we have ampere, V, SOC, and temperature. As I told, simple BMS will have these things to be taken care. So this is readily available in Matlab. And after this, and this basically a single cell characteristics. That is what I was talking earlier. Battery SOC level. So this is a single cycle level that is slowly discharging at 10 amp. Okay, while your current, that is pulsating current, being utilized. So 10 into this, that is 4, total 40 AH capacity is there. So based on this graph, you can also create this graph by just changing. Once you go to this, your R table and C table is there. You can change the value based on your cell, whether it is a crystalline, prism based lithium cell, which kind of cell you are using. So based on that, if you go into the detail of the cell data sheet, then you have to put into the Excel and just load your data to this particular table, and your model is going to work. Okay, it's very simple. Fine. Let us go back. There is another model, that is temperature model. Temperature model is also of varieties given. And in temperature model also based on lead acid, based on lithium ion, lithium phosphate, nickel metal hydride, everything is changing. So here the comparison is given with lithium ion temperature dependent battery model, that is with temperature and without temperature. Fine. Ultimately, both the batteries are compared here with the voltage, current, SOC, and temperature. This is also readily available in Matlab. Okay. What I want you to look into is, let me go to these examples. In the example, you will find readily available energy management systems, for electric drives, that is with 12.8 volt 40Ah lithium-ion cells. This is what we had seen. Okay, and energy management system for a hybrid. See, as I told, now battery management system will have different criteria. If you are battery operated electric vehicle, it will be different. If it is hybrid, the combination of battery and some fuel cell, battery and petrol. So again, EMS is going to be different, right? So there are various models are given. You can refer them, and just I'll suggest that try your hand with energy management system for battery EV. This is with temperature, and just put the table. Okay, select the cell if you are expected to design the battery management system, go to the manual of the cell and put the data inside this, and you will get your model work. There is nothing to do much with this, Apart from this, if you know the model, as I told here, simulating modeling. So once you decide the cell, your battery model is ready. Once you decide the cell, your temperature model is ready. Okay. After that, you should create a logic. Okay, in which you want to control your SOC, in which you want to control your current, that is in case of charging and discharging, and how much amount of temperature you want. So basically from 45 degrees Celsius to 72 degrees Celsius, that is at max, for any pack we are relating in a thermal model. So if it exceeds 72 degrees Celsius, then we stop it. So some kind of logic you have to create, and that logic depends on mainly three things. One is your type of vehicle, that is your two-wheeler, three-wheeler, and four-wheeler, its drive cycle. Okay. Second thing depends, that is particular regenerative or not. That means if you want the reverse current to flow in your battery or not. That is what V2G and G2V criteria you can consider. That is the second thing. And third thing is how much amount of current you want to draw. That is your C rate. Whether it is 1C, 2C, 4C. That means whether your battery pack is fast charging, slow charging. Okay. So people are talking about fast charging is better, but it's not so. And you have to estimate based on BMS. Every BMS cannot allow your battery pack to get fast charging. Okay, because BMS has decided its overcurrent protection, and that logic you have to go and create within the state flow. Okay, you can download the state flow, this kind of graphs you can create, and you can have your own logic for the battery management system. I hope you are understanding much more with this. And after creation of the model, you can generate the code from the model file. Okay, connect your algorithm, go to the hardware, and prepare your own BMS. Right? Okay. I want to show you some video over here. Just a minute. Can you hear the sound of the video?
Sir,
No,
Can you
sir.
hear the sound?
while sharing the video, you have to include system audio. No, sir. While you sharing the video, you will get one tab, which is written like that. One button is there. Include system audio, and you can hear your system voice. Very again. No, sir, no. Stop sharing first, then share it again. While you sharing, you will get one button called system audio, includes system audio.
Say this battery system is part of an electric vehicle part. Say the battery is
Is that okay? Do you get?
and the outside temperature is 15 degrees Celsius.
Yes, sir. Yes, sir.
So start driving for a while and stop and charge the battery. Finally, the battery is at rest and the balancing cycle kicks in. How do we know that during these three typical usage stages, the battery pack remains within recommended electrical and thermal limits? What if the temperature is 40 degrees Celsius instead of 15? How about if the initial state of charge is 30%? Will an aggressive drive cycle cause an undervoltage situation? A model allows the vehicle designer to test all these situations in simulation without risking causing damage to the real battery. This is the BMS model in Simulink. The battery and its management system are inside this model reference. On the top left, we define the different driving scenarios that determine the test sequence provided by the subsystem on the bottom left. The green lights at the top right indicate whether there has been a fault, for example, that any cell has reached a poor temperature condition. The system itself has a model reference representing the BMS ECU with its various monitoring and control algorithms connected to a block with a representation of the battery pack and associated circuitry and peripherals. This model contains two versions of the battery pack. A small one with just 6 cells connected in series, and a larger one with 16 modules, each module containing the 6-cell series string. In all cases, we model just one parallel string. Let's start with a description of the battery pack and its peripherals. The variant subsystem on the left contains the two versions of the battery pack mentioned before, the one with 6 cells and the large one with 96 cells. Let's take a look at the small one first. This battery pack is modeled in SimScape, where the component color tells us its physical domain. For example, blue indicates electrical and orange indicates thermal. We can see that the 6 cells are connected in series and can exchange heat with one another. The thermal layout is asymmetrical, with cell number 6 at the bottom insulated on one side, so no heat can dissipate in that direction, and cell number 1 at the top exposed to the outside atmosphere and therefore getting rid of the heat by convection. This asymmetry will be responsible for a significant temperature difference among the 6 cells. So what makes each unit cell representative of a real-life lithium-ion chemistry, say nickel, manganese, cobalt, or NMC? Well, inside each cell, there's an equivalent circuit whose topology and parameters should give me a response equivalent to the one I would observe experimentally. The equivalent circuit components should also include temperature, SOC, and possibly aging dependencies. If you're interested in cell characterization, a detailed account on how to perform this parameter estimation on battery cells is available on our website, searching for battery modeling. Next to the battery pack, there's a subsystem with a passive balancing circuitry. Commanded by the balancing logic from the BMS algorithm, these switches selectively close when their corresponding cell needs a partial discharge to lower its SOC. Maintaining the battery cell modules in balance allows me to better utilize its total storage capacity, as we will see in a few minutes. Another important element of the plant model is the set of charger and inverter contactor circuitry. Prior to connecting a battery pack to a charger, it is important to pre-connect them via a resistor to prevent an excessively high current from rushing into the pack and potentially damage it. This pre-connection needs a special sequence that we will show when we describe the BMS algorithm. Finally, the last piece of the battery plan that we model here are the charger and the load, both simply represented here by current sources commanded to follow the charging and driving profiles from the source block at the model top level. Let's now focus on the BMS algorithm. This part of the battery management system monitors, protects, limits, and reports measurements from the battery pack. The subsystem on the left uses individual cell voltages and temperatures to calculate maximum allowable charge and discharge current levels. When a cell is at low SOC, its voltage is low, and it is important to prevent the cell from delivering a large amount of current, since this would cause an excessively large voltage drop that could potentially be below the cutoff voltage specified by the cell manufacturer. Comparing the minimum cell voltage in the module against this lower threshold and dividing it by the maximum internal resistance value calculated for this cell, we can compute a voltage-based current threshold. We also know that it is important to limit current delivery or intake when temperature is too high or too low. Using a lookup table with a rising or falling S-shaped profile, we can specify a current threshold based on temperature and modulate the allowable current delivery. This is very important to avoid physical damage to the cell materials at high temperatures, both during charge and discharge, and at low temperatures during charge, since doing so below freezing temperature is not allowed. These two thresholds are then compared against one another, and the lowest becomes the current limit. The subsystem labeled state machine defines the main operating state of the BMS. It is represented here using state flow, a Simulink add-on toolbox meant for designing state logic. In state flow, we use components representing states that are active or inactive depending on the conditions. And the text we write inside the state is code that executes on entry, during, or an exit from the state. The state machine has 4 parallel states. Parallel here, meaning that they can be active at the same time. The first one defines the variable BMS state, which indicates standby, driving, charging, and fault. Charging comprises constant current and constant voltage stages. The second state switches the fault state on in case of a current, voltage, or temperature value reaches an unsafe level. The third and fourth states define the contactor on and off switching sequence for the charger and inverter. This is needed to avoid an excessively large current inrush at the beginning of the charging stage. Knowing how much longer...
Is everything okay, sir? Going fine?
Yes, sir.
Okay.
We will be able to drive our car before we need to stop for a recharge depends on accurate estimation of the battery SOC. This is of great importance, and it is much more challenging than in the case of conventional vehicle fuel gauge design, where the measurement is direct. In battery systems, we do not measure state of charge, which is not directly measurable. We actually measure something else and hopefully relate that to the SOC. The third subsystem contains 3 different methods for state of charge estimation. In practice, the BMS developer would only use one of them, but here we present all 3 to illustrate their individual merits and limitations. The first method, known as Coulomb counting, consists of integrating the current that enters and leaves the cell to keep track of the state of charge over time. A benefit of this method is its simplicity and very low computational cost. Its drawbacks include the accumulation of current sensor error and its inability to recover from a wrong initial condition because of the lack of feedback from voltage measurements. The second and third SOC estimation methods implemented here are the unscented and extended Kalman filters. Both are variations of nonlinear Kalman filters, and they rely on a model of the unit cell to predict the terminal voltage resulting from a current stimulus, estimating the internal cell states, the SOC among them, by comparing this prediction against measurement of the terminal voltage. The choice between EKF and UKF is typically made based on the severity of the system's nonlinearity. In this case, the only nonlinearity present is given by the OCV-SOC relationship, and it is a mild one, so it is expected that the EKF should give adequate results. The Kalman filter algorithm has two parts, the state update and the measurement update. The state update predicts the current state based on the previous state value and the input, and the measurement update corrects this prediction using newly acquired data. The cell model we use is implemented here as a Matlab script and corresponds to the equivalent circuit we use to simulate the battery pack. The next task to consider is balancing. It is important to keep individual battery cells roughly at the same state of charge. Otherwise, the cell with the highest SOC level will limit the amount of charge that we can put into the pack, rendering the system underutilized. This state logic calculates the voltage difference between the highest and lowest cell voltages and, based on whether this difference exceeds a design value, activate passive balancing. Balance command is a Boolean vector that indicates which bleed resistor to activate so that the cell SOC is slowly reduced. Doing this with all cells but the one whose SOC is the lowest eventually makes all SOCs converge within a prescribed tolerance. Let's now take a second look at the simulation results. In this driving, charging, balancing sequence example, we first observe the individual cell voltages changing as a result of current flowing in and out. At the beginning of the simulation, they are slightly different because we initialize the model with a slight SOC imbalance. Towards the end of the simulation, the values converge towards one another as a result of the balancing procedure. And how about current? Look at the charging period. During the constant current stage, the current is derated because the maximum module cell voltage is high enough compared to a prescribed 4.4 volt limit that an excessively high current could drive the voltage beyond the threshold, significantly limiting the life of the battery. Since we calculate the limits based on the maximum resistance value within the battery cell lookup table, we're being conservative. A less conservative current limiting calculation could use the actual battery cell resistance at the estimated SOC and temperature, since this information is available at all operating conditions. The temperature traces show a significant discrepancy among the hottest and coldest cell. The reason is mainly the asymmetry in the module layout in terms of thermal behavior. Cell number 6 gets significantly hotter than cell number 1 because it is thermally insulated on one side. Even when the maximum temperature reached during the simulation is not of immediate concern in terms of safety, the temperature difference exhibited here will eventually cause a much faster degradation of cell 6 compared to cell 1, leading to an undesirable unevenness in cell condition. Hence the need for active thermal management to keep thermal differences within a few degrees Celsius. The graph at the top right shows 3 SOC estimation traces of the same battery cell, each performed with a different method. Yellow corresponds to Coulomb counting, blue corresponds to UKF, and orange to EKF. The initial SOC in the simulation is 75%, but the SOC estimators were initialized to 80% to assess their capability to recover. It is apparent that Coulomb counting never does, because it has no way to realize it is wrong due to the absence of voltage information. Both Kalman filter algorithms, on the other hand, recover from the initial error within the first hour of simulated time, with the EKF slightly outperforming the UKF. And finally, the other two scopes indicates the BMS state and each of the 6 balanced command signals, respectively. In summary, we've utilized Simulink, Stateflow, SimScape, and control system toolboxes to design a battery management system using modeling and simulation. Now I'll turn it over back to Chirag.
So this is what simulation I had learned from MathWorks, and that was too long to cover in practical approach with this. So that is why I thought that let me have the video from which I have learned. I should represent it to you. Okay. Am I audible? Fine.
Yes, sir.
Okay. Now let us go further with the software design. What is better, software or hardware? Whether you will go with simulation of Matlab or directly with the hardware. So let us go one by one. In case of software, this state flow, logic control, you have to go with modeling. You have to create your algorithm. You have to have understand the cell-to-cell combinations, the different parameters like CR, that is your conductive resistance between the electrodes, and you should understand the particularly the how to measure SOC, what type of algorithm you will prefer. Then getting the result, you will go to buy the hardware, right? After buying the hardware, you will try to have the combination, what happened with the software and what happened with the hardware. So you will try to do bifurcate the differences between the two. You will try to have the nullification of the errors, and ultimately it will take your time. But what happens in case of hardware? Directly select the hardware for the BMS. Follow the manual given by the hardware manufacturer, whether how much amount of temperature you want to control, what is the current limit. As we know that in case of Arduino based, our students used to connect the different relays for operating the motor, for fan, tube light, television, etc. So on that they select different current relays based on the ampere capacity. So similarly, you can select the ampere capacity or ampere over current, over voltage, whatever you want, that is through hardware. Follow the manual, rectify error, that is, the minor errors which are generally in case of connections. And so you can judge it by the given schematic diagrams and get the result from the hardware, right? So the difference between software and hardware is what I personally believe is, if you are designing the battery management system, if you know the cells, if you know the amount of current you want to draw from the battery pack, how much amount of your current you want to discharge from the battery pack, how much amount of current you want to charge, you want to give into the battery pack. If all the parameters are known to you, like temperature is known to you, voltage rating is known to you, kWh is known to you. If everything is known to you, you know the method, whether you want to go with active balancing of cell or passive cell balancing, that is also known to you. So it is better not to go to the software, don't waste your time, because there are many companies who had already worked for this, okay, and they had developed their hardware boards, okay, and they had given the manual. Based on that, you can directly purchase those hardware and you can connect to your battery pack. Or rather, after connecting, if you have any issues, sometimes in our experiment we had found that there are some issues, like we want to add something apart from the given parameters of the manufacturers. We suggest them to incorporate them, and later they'll come with suggestions from the manufacturer that don't use this hardware board, better you go with this PCB. This kind of suggestion you will get from the manufacturers. Okay, so this is my personal feeling, and this is out of my experience, that we should not waste much time. If you are really keen to have some battery management system for your own battery pack, whether it's lithium, whether it is lead acid, anything. Okay, and still, if you are concerned with the cost, okay, in case of hardware, then I'll suggest for trying an experiment with the UG students, it is better to go with the Matlab, and readily models are available, so you can go and think of it. I'll show you how to get the hardware for BMS, and I had referred some site earlier also, and based on that, we used to select, the particular. So this is Texas Instruments. It is known to you. Similarly, Intel is also having, and NI is also having their own hardware. Okay, once you log into this battery management system based Texas boards, you will get selection for subsystem over here. Okay, in which there is a 400 volt battery pack, passive balancing. Once you click on this, it will have the options. Similar things are there with Intel also. They are giving different combinations. Fine. Suppose I want 12 volt or 24 volt. Let us say I am designing my BMS for cycle, okay, and which is at 24 volt battery pack, and I want passive balancing because it's the simplest and cheapest system. So once I'll click on this, it will give you all the idea and how to connect your board, everything. Okay, so this is already given to you. Fine. And once you purchase this, along with that, there will be a manual. Like our, when you simply buy any laptop, you will have the manual how to switch on, starting from switch on to how to upload the software. Same thing is there. If you buy this kind of BMS from any manufacturer, they'll give you manual, which includes schematic diagram, reference guide also, and the detailed design. So that is why I say, why should we waste in designing the simulation? Why should we not directly try the hardware? And this hardware is costly, not much costly, because it depends on your passive and active balancing system, how much amount of voltage you want. Okay, I'll take to one example of let us say battery control unit, not battery control. Let us go with 2448 volt. And in this, there is a digital processing system is connected. You can go with the schematic. It's very simple. With your connection, they are showing where to connect, which wire we should connect. So if you go to Bharat AC 001, Bharat DC 001, along with that, they will give you, this kind of connections also. Fine. So this is a two-way connection, whether it is your onboard charger or off-board charger. The particular connections are already given by the manufacturers. Yeah, of course, you want, it is said, somebody said that if you want your own algorithm to be practiced, or you want your research paper to be published, you are in hurry to have, your guide or supervisor to show that I am doing, something good for the software side, and it is without any cost. So it is okay, but already so many things has been done with BMS, right? So here all the diagrams are available, the voltage connections and the plug, whether it is with plus or minus, that is already given. All the connections of cell to cell is already described and how it is there. So these boards are already giving you everything, everything, right? So simply you have to do is ti.com solution battery management system, and you can refer. There are battery monitors and this control units depending on the number of cells is also given. If you have 3 to 6 cells, you should choose this. If you have 16 cells, you have to choose this. So similar combination you will get from for different number of series and parallel cells. Okay, and the hardware is readily available. Okay. So this is what I want to say. With active balancing also, in case of active balancing also, you can find, though it is a little bit complicated, you will be able to connect all. Okay, the active charge transfer block is there, and our BMS board which you are purchasing, that shows the output connection with DC-DC supply in case of charging system control. We have, so this is simply your base information. Then cell safety and temperature sensors are there. So what number of temperatures you are, I mean the sensors you are connecting, that can be incorporated. Then they had already given with these schematic diagram how many temperature sensors you can connect with this. So along with number of cells you are connecting in parallel and series, you can choose your BMS hardware block, right? So I hope you are understanding, the differences between why we are lacking from different selection, and it is matter of daring, how to work on that, and it's very easy. So people are feeling that battery management system is something different, complicated, but it is there for us, because we had not touched those. But those people who are already working in this for the last 10-12 years, they know very well. So they had already designed the boards, and one of the board this is from Texas for 15 cells. Okay, so you will have pack minus, pack plus. This is for charging connection. This is for battery connection, and you can connect 15 cells over here. Okay, and your system mode bus connection over here. Then auxiliary inputs, like if you want to go with some auxiliary system, as I said initially, so you can connect this. This is actually, this is a single cell combination. Actually, this is copyrighted block, so that is why I had darkened it, but I'll show you how it's done. So this is a plus connection, which is already set, plus battery, okay, which is going inside the controller unit, and minus, which is also going to another combination. These are different cells communication. So when you have your charger, charging gun, so inside the charging gun you will have 16, 17, 3 connection, etc. So based on that, you will have the CAN bus connection, and this is with your charging point. Okay, similarly you can have your different communication with the charging points also. And this is I had taken from the Intel website, and it is already available. You can search them, but I cannot show you because of copyright. Well, the earlier board which I had shown, the hardware board, has different block sections of the particular board, which says a pre-charge circuit, boot circuit. See, basically in any kind of BMS there will be first, that is the sleep circuit of the battery management system. That means if your battery is at sleeping mode, that means your DOD is below 20%, what you should do. And similarly, the pre-charge state is there. That means you need, below 1C. Suppose your battery pack is 1C, and then you need to go below 1C. So in that case, you have to go with pre-charge, and there will be awakening circuit also. Some combinations are there with boot circuit, awakening circuit, sleep circuit. You can display your readings, whatever is there. That is your SOC, current, temperature, and the counter also. Okay. So you can connect your display with this. That can be LCD 16:2. AFE is a kind of algorithm used, and The manual will give you, the software also, so you can directly see what is happening inside the board. Here you have to connect the cells. This is high current, that is nothing but charging and discharging connection. So this is basically your board in which TDAS 792. So you can connect your SM bus over here, and you can see through softwares what is happening inside the board. Your charging is there with pack minus and pack plus. This is with the load, okay, and different cells are connected. So this battery pack combination. This is our board which I have shown. This one, okay, this one. So this is your battery and your load is there. So reverse control system is also there. You can add your facility, and the different boards are available with the Texas NI as well as with Intel. Okay, this is for charge test. This is for discharge test. So in that case, we connect the load instead of charging, we connect over here. So some electric vehicle, whether it is with lithium-ion 3-wheeler or lithium-ion based 4-wheeler, they have one manual switch over here with this controller. Okay, and this manual switch is available at the dashboard of the car or at the 2-wheeler. So you can switch on. Once you switch on, that means your overall communication is done from battery through this board to the motor. Okay, and there will be another packs also which are also communicating with controlling based on braking and acceleration. Okay, this is the software available. You can download once you purchase the hardware. They'll give you the link to download the different BMS studios. Some of you might have used Code Composer Studios for DSP. So similar kind of software is there. So in which you will have all the details, whether it is USB connection with your particular controller, what is the potential at the battery pack, how much of amount of current you want to draw, what is the life period, everything, current aging, even with what aging you are going to have, what temperatures, individual cell to cell temperatures are there that can be monitored into your PC. So voltage, potential, current, everything can be seen in the softwares, and that is what we had done for developing a 2-wheeler battery management system. Okay, so you can do this fine. Once you go with that, you will have the selection of the particular criteria, whether you want wireless charging, whether you want to go with the charger, which is of Bharat AC or DC. The options are available, whether AC charger or DC charger, and reference design criteria is also given inbuilt. So the protection also you can select from here. Once you click on this, that is available. Okay, it will open in detail, the support targets with that. If you don't want to select this, you can have the flow with your battery manufacturer. So if you are purchasing lithium-ion battery pack, there is inbuilt BMS system. But in case if you are creating your own lithium pack and you want to attach your BMS hardware, so you can do that also. And similarly, this is also helpful in reverse way. The reverse way, I mean that if your battery pack is having error, basically there is a code, different codes through light we can understand. That is what in Nexon and eVerito that is given. So based on that code, you can understand which issue is there. And once you connect your computer to BMS inside the car, it will tell you the error, and you have to just you are updating or resetting your software. You are taking the backup. So similar kind of thing is there. You need to do that, and that is very helpful in case of skill development. Okay, and these softwares are free of charge available. If you want your students to share, you can share to the Texas Instruments. Then in BQBM, if you write BQ Studio, the softwares are free of charge available. Of course, that is with the student version and professional version. Okay, that is a limitation. Inside this software, you will have the chemistry tab also, data memory tab also, FET entry, that is your control system, of which kind of control you want to prepare. Then calibration is also available with cells, that is parallel, active balancing, passive balancing, and many things are available. So, I had seen people striving for designing the BMS, but I'll suggest that you go directly with the hardware instead of wasting time in simulation. Okay, you can take the thermal images and verify your temperature records. Okay, and this is up to 72 degrees Celsius we can verify. So in basically when I was working with the LD College of Engineering, we had the FLIR thermal camera. So based on that, we had done some experiments. Actually, I had taken this from the readily available. I had not shown my experimental result over here, but you can do the same. Okay. For testing of BMS, there are various testing agencies, NABL accredited, available in India also. You can go to ARI also. This ADA Baroda has also started some battery testing. Especially what kind of test they used to do is some voluntary tests and necessity tests are there. So mandatory test includes over current protection, over voltage protection, under voltage protection, over temperature and under temperature. Out of that, I'll say that generally people go with over voltage and under voltage. Okay, because overcurrent will be taken care by during the charging, and the fuse are already there with the battery, so they take care. So at the initial stage, if you want to save money, if you want to have some control on the cost of your R&D, then go with this over voltage, under voltage, and over temperature testing. Okay, I've taken all this from these various references. Okay, so I keep up to here. Now, if you have any questions, you can drop. I think I'm 3-4 minutes early. Is it so, sir? 3 minutes early. Hello, am I audible? Yes, sir. If you don't have any question, then I'll ask the question.
Participants are requested, if you have any doubt or any question, you can ask the question.
Hello, sir.
Yes.
Sir, that C rate you mentioned, does that have any effect on discharging also? Because you have mentioned about the charging portion, that how C rate is affecting charging. But how does it affect the discharge of the battery?
Yeah, definitely. The C rate affects the discharge rate also, because sometimes practically we had seen that your dashboard of vehicle says that you have sufficient charge, right? But in case of discharging, while you are running your pack, the immediate potential, like let us say the 48 volt pack is there, and initially it says 52.2 volt, and suddenly while after even within a 1 minute you will find that your potential drops. So C rate combination is basically like the limitations given to the battery users, that this is the minimum amount of charging current required, and this is the maximum amount of current you can take out from that. So based on C rate, it affects the temperature, and based on C rate, it affects your discharging capability. If it is passive balancing, then it's very serious. But in case of active balancing, it manages. So there is not much issue with that.
Okay, sir.
Okay,
and subsequent also affect that self-discharging rate, na, sir?
Yes. See, basically self-discharging rate is concerned with ESR and EPR. So practically what we had found is, while we had tested the 2-wheeler, 3-wheeler and 4-wheeler battery pack, and after having full charge, 100% SOC is there, and we kept it for 2 days in idle state without using it. So within 2 days, we had observed that there is at least minimum 8% discharge is there. So if you are using your battery, that is fine. But with DOD, 20% discharge is going to be considered in life cycle. But if you are not using your battery pack, as per our records and data we had seen, it says at least 8% of battery pack is going to be discharged in case of lithium ion. But in case of lead acid batteries, which earlier company VRL and all they are using, so in that case we had observed more than 15% self discharge.
Okay, sir.
And that is, self-discharge, basically. So based on C rate, it varies, because if your C rate is very low, then definitely there will be larger amount of self-discharge.
Okay, sir.
Any other participants would like to ask the question? 16 number has raised the hand. 161 number. 16 number has raised the hand. Have any doubt? FDP 016 number. Okay, sir. So thank you for giving such a nice speech. And now we will meet sharp at 11:30. So now we will start the next session at 11:30. Thank you, Chetan sir.
Thank you.
सर सेम वो रहेगा कि दूसरा आईडी रहेगा? हेलो सर.
हाँ.